Hello, welcome. In this short video, we will derive the sample mean as the minimum variance unbiased estimate of the parameter in a linear model. That is, given the linear model as x of n is equal to a plus w of n, where w of n is a Gaussian process with the mean 0 and variance sigma square. We want to prove that the minimum variance unbiased estimate of A is given by the sample mean, that is 1 by n summation n equal to 0 to n minus 1 x of n. Note that here n value changes from 0 to n minus 1. So this is our goal. That is, the estimator A hat is equal to the sample mean. So in order to derive this relation or this expression, we want to start with a linear model for the estimator. That is, A hat is equal to the summation n equal to 0 to n minus 1 a n into xn. So this is a linear model for the estimator. Now we want to find the values of a n under the criteria that this estimator minimizes the variance and the bias is 0. So in order to construct the cost function, first we have to derive the variance of this estimator A hat. Variance of estimator A hat is given by the difference between expectation of A hat square, that is for second moment of A hat, minus expectation of A hat whole square. And from the definition from the given linear model, we know that x of n is a Gaussian process with mean a and variance sigma square. So by using so this is equal to expectation of summation n equal to 0 to n minus 1 a n into x of n. And since a n is a deterministic quantity, we have summation n equal to 0 to n minus 1 a n into expectation of x of n. And since expectation of x of n is equal to a, we have a into summation n equal to 0 to n minus 1 a n. Therefore, the mean of the estimator A hat is equal to, or expectation of A hat is equal to a times the summation n equal to 0 to n minus 1 a n. Let us call this equation 1. Now let us determine the second moment of A hat square, which is equal to expectation of the summation n equal to 0 to n minus 1 a n x of n whole square. This can be rewritten as expectation of the product of n equal to 0 to n minus 1, basically product of two sums, that is summation over n's and the summation over m's, m equal to 0 to n minus 1 a m x of m. And this should be equal to, and since the expectation is a linear operator and an's and am's are deterministic quantities, we can rewrite this expectation of summations as summation of n equal to 0 to n minus 1 and again summation m equal to 0 to n minus 1, and taking the expectation inside, we have an into am into expectation of x of n into x of m. And given that xn and xm are independent identically distributed random variables, the expectation of xn into xm becomes, that is expectation of xn into xm is equal to expectation of x square n for n equal to m, and is equal to expectation of xn into expectation of xm x of m for n not equal to m. So by using this definition, we can rewrite the summation as summation n equal to 0 to n minus 1 summation m equal to 0 to n minus 1 a n into a m into, by using this definition, we have expectation of xn square, expectation of x square of n for n equal to m. That means this sum can be basically broken down into one index n, and the next for n not equal to m, we have the other summation, which is given as summation over n equal to 0 to n minus 1 and m equal to 0 to n minus 1 for n not equal to m, a n into a m into expectation of x of n into expectation of x of m. we know that expectation of x of n and expectation of x of m are basically a's, that is, this is a square, and this is equal to expectation of x square of n is equal to basically variance of x of s n plus the since the definition of variance is the second moment minus the square of the mean, this is variance plus the square of the mean, that is expectation of x of n whole square, and this is equal to sigma square, and this is equal to a square. So by using this definition, we have expectation of a hat square is equal to summation n equal to 0 to n minus 1 a n square into sigma square plus a square for the first term, and for second term we have double summation for 1 for n equal to 0 to n minus 1 and m equal to 0 to n minus 1 a n into a m, and n not equal to m, that is n not equal to m, and this is equal to a square. And the second condition, that is in order to construct the cost function, we have the variance term, that is variance of a hat square, variance of a hat is equal to the difference between the second moment minus the square of the first moment. This is equal to the summation n equal to 0 to n minus 1 a n square into sigma square plus a square plus the double summation, that is n and m, when not equal to m up to 0 to n, from 0 to n minus 1 a n into a m into a square minus a square, that is for expression of a hat square. So this is the cost function, and we also have another condition, that is the estimator should be unbiased, that is expectation of a hat minus a should be equal to 0. Basically the function L consists of the parameters a hat and lambda is equal to the combination of the original cost function, that is variance of a hat, plus the constraint, that is bias, should be equal to 0, that is lambda into expectation of a hat minus a. So this is the combined cost function. So by using the definitions we derived, we can rewrite this as summation n equal to 0 to n minus 1 a n square sigma square plus a square plus double summation n equal to 0 to n minus 1 m equal to 0 to n minus 1 n not equal to m a n a m a square minus a square plus lambda into summation a into summation n equal to 0 to n minus 1 a n minus a. So this is the combined objective function. Now in order to find the optimal a n's, that is we want to basically minimize this cost function, argument minimize a case for L of a hat comma lambda comma a n's. So we want to minimize this cost function, that is we can easily do that by differentiating this one with respect to a n. This we want to basically differentiate the cost function a hat comma lambda comma a n and put it equal to 0. So basically by differentiating this function with respect to ak, we have the following results. It should be equal to derivative of this term with respect to ak should be equal to 2 times ak into sigma square plus a square, and this one when there is only one ak, and since n is not equal to m, this should be equal to basically the derivative should be equal to the summation m equal to 0 to n minus 1 and m not equal to k a m into a square. That is the derivative of this one with respect to ak. This derivative should be equal to 0, and this one should be equal to plus lambda a into 1, and this is equal to 0. Let us call this equation 2. Now by differentiating the cost function with respect to lambda, that is dou lambda of the cost function a hat comma lambda comma ak, putting it equal to 0. By putting it equal to 0, we have the summation, and basically this term should be equal to 0. That means a into summation n equal to 0 to n minus 1 a n minus a is equal to 0. This basically implies the summation n equal to 0 to n minus 1 a n is equal to 1. call this equation 3. So by using this equation 3 and inserting it in equation 2, we have 2 into ak into sigma square plus a square plus, and since the summation is equal to 1, this should be 1 minus ak into a square plus lambda into a is equal to 0. Now by rearranging the terms that are related to ak, we have ak into 2 sigma square plus 2a square minus a square. And the rest of the terms are plus lambda a plus a square is equal to 0. Therefore, ak is equal to a square plus lambda a divided by 2 sigma square plus a square. Let's call this equation 4. Now by using this definition, result and the equation 3, we can clearly see that it is equal to a square plus lambda into a divided by 2 sigma square plus a square summation n equal to 0 to n minus 1. This basically means that this is equal to a square plus lambda is equal to 1 by n into a square plus 2 sigma square. Therefore, lambda is equal to 1 by n minus 1 into a square plus 2 sigma square by n and into 1 by a. This is the value of lambda. Now by inserting this value of lambda in the equation 4, that is the value of ak, we have lambda into a is basically equal to this numerator, which is equal to ak is equal to a square plus 1 by n in minus 1 into a square plus 2 sigma square by n, which is equal by divided by 2 sigma square plus a, which is equal to, a square and a square will get cancelled, and we have 1 by n into 2 sigma square plus a square divided by, of course, this is a square, 2 sigma square plus a square, which is equal to 1 by n. Therefore, the optimal value of an is equal to 1 by n, and hence the estimator a hat is equal to summation n equal to 0 to n minus 1 by n x of n, which is basically equal to the average, that is the sample mean. Hence the sample mean is the optimal estimate for the parameter a. Thanks for watching.